Hello everyone, this is Dr. Webb and welcome to the next Abstract Algebra 1 video. So in this video we are going to keep our discussion about cyclic groups going. So just to recall, we say that a group is cyclic if it is generated by one element. So there's everything in the group we can think of as being that element applied to itself some number of times. So our goal in this video is to classify all the subgroups of a cyclic group. So if we start off with a group that's cyclic, what can we say about the subgroups of that group? So we're going to start doing some reviewing of things that we proved in the last video about cyclic groups. Recall if G is a group and E is our identity and A is something in the group and it has order less than infinity, well then A applied to itself k times is equal to the identity if and only if n divides k. So k is a multiple of n. We get A applied to itself I times is going to be the same as A applied to itself j times if and only if I is congruent to j mod n, or again n is the order of A. And if we look at the cyclic group generated by A, well, so it has precisely n elements, and those we can think about those n elements as just being, the first n powers of A starting with the 0th power, which gives us the identity. So it's the identity A squared, A cubed, all the way up to A to the n minus 1. And then if we took one more power of A, if we applied A to itself one more time, then we'd have A to the n, and that sends us back to the identity. And this is sort of in my mind, this is where the term cyclic comes from, is that you start with the identity and then you start applying A to itself and it just starts cycling through everything in the group. And then when you get to the last one, A to the n minus 1, if you apply it one more time, the cycle closes and it goes back to the identity. So if any of these facts, if you need to go back and review any of these, I'd say go back and rewatch the last video because these were the major things that we proved in that video. So first thing we're going to prove right now is if we have an element A whose order is n, and if we have D as a divisor of n, and D is a positive divisor of n, then the order of A to the D is going to be n over D. And the subgroup generated by A to the D is going to be precisely the first n over D powers of A to the D. So that would be the identity, A to the D. A to the D applied to itself is A to the 2D, all the way up to the last one. If we apply A to the D to the n over D minus 1, we get A to the n minus D. So to be precise, this is equal to, if I take A to the D and apply it to itself, n minus d minus 1 times. And if you multiply the d through, you can see that it simplifies down to A to the n minus d. Okay, so let's prove this. So first we're going to prove the first part of the statement, that the order of A to the D is n over D. And so we're going to prove that in 2 steps. So first we're going to notice that if I take A to the D and then apply it to itself n over D times, how many A's do we have here? Exactly A to the n, which gives us the identity. And so what this means is that if I raise A to the D to the n over D, I get back the identity. And so this means that the order of A to the D has to divide n over D, right? Because we have found a power of A to the D that gives us the identity. And if I take any k that's less than n over D, well then D times k is less than d times n over d, because k is less than n over d, which is equal to n. So d times k is less than the order of a, and so that means that a to the dk is not equal to the identity. So n over d is the smallest. It is a power that works, and it is the smallest power that works, because if I apply any other power, I'm not going to be getting enough a's to get back the identity. And so this shows that the order of a to the d is exactly n over d. Okay. And now let's go and prove the second part. Well, now that we know that the order of a to the d is equal to n over d, well, now if we take the generator of it, this is just going to be all the powers of a to the d up to n over d minus 1. And so by what we saw before, a to the d is going to have n over d elements. The first one is the identity, and then it's all the powers up to a to the d, raising it to the n over d minus 1. And as we talked about before, this last one is precisely a to the n minus d. Okay, and so again, this is relying heavily on what we proved in the last video. Okay, now we get to this. This really is the most important theorem, the most useful theorem in this video. Everything else that we're going to do after this completely relies on this. So again, we're going to have A is an element with order n, and we're going to take k to be some integer between 0 and n. Then the order of a to the k is going to be n divided by the GCD of n and k. And the subgroup generated by a to the k is going to be the exact same as the subgroup generated by a to the GCD of n over k. Okay. So to make things simpler for us, let's let d equal the GCD of n and k. Okay, so first, let's prove the first statement, that the order of a to the k is equal to n divided by the GCD of n and k. And so for that statement, we can write since d is the GCD of n and k, we can write k as d times some other positive integer l. And so since d is the GCD of n and k, l can't divide d, can't have any common divisor other than 1 with n. And this is a fact from number theory. And so this means that the GCD of n and l is equal to 1. Otherwise, if it wasn't equal to 1, then we could get a divisor bigger than d that divides both k and n. And so since d is the greatest common divisor of n and k, that means that whatever l is, its GCD with n has to equal 1. Okay. And so then if we take a to the k and raise it to the n over the d power, well, this is really equal to a to the d times l raised to the n over d power, which gives us a to the d's cancel here, n times l. So what's important is that this is a multiple of n. And so since we have a multiple of the order of a, this is going to give us back the identity. So this tells us that the order of a to the k divides n over d, because n over d is a power that makes it the identity, and so its order has to divide that. So next we will show that n over d divides the order of a to the k as well, and so if they divide each other, that means they have to be equal. So let's let t equal the order of a to the k. Well, that means that a to the k to the t is equal to the identity. And this means that n has to divide k times t. And so then we have n divides, we can think about k as being d times L times t. But we know that the GCD of n and L is 1. And so if the GCD of n and L is 1, this means that n has to actually divide d times t. And so if n divides d times t, so we can say n times s equals d times t for some integer s. And then now we can divide both sides by d because n is a multiple of d. And we get that n over d times s equals t. And so t divides n over d as well. And if they divide each other, this means k is equal to n over d. Okay, so that completes the proof for this first part. Now we are going to focus on the second part, proving that then the subgroup generated by a to the k is equal to the subgroup generated by a to the GCD of n and k, or a to the d. So let's clear up the space first. That's better. Now recall that k is a multiple of d, so k is equal to d times L. And so we're going to prove this in two different ways. The first way is more of a counting argument, and then we'll go back and we'll do more of a number theoretic way of proving this. In the counting argument, what we're going to prove is that first, notice that k is a multiple of d, and so this means that a to the k is an element of the subgroup generated by a to the d, because the subgroup generated by a to the d is simply all of the powers of a to the d. And so we have a to the k is inside a to the d. Now, this also then means that since a to the k is inside the subgroup, I could apply a to the k as many times as I want to itself, and because the subgroup is closed, I'm still going to be inside the subgroup generated by a to the d. So the subgroup generated by a to the k is a subset of the subgroup generated by a to the d. Now, how many things are inside the subgroup generated by a to the k? Well, we just figured out that the order of a to the k is equal to n over d. So since the order of a to the k is equal to n over d, this means that the order of the subgroup generated by a to the k is also equal to n over d. Well, similarly, the subgroup generated by a to the d, its order is also going to be n over d. And so this means that the subgroup generated by a to the k has the same number of elements as the subgroup generated by a to the d. And so since they have the same number of elements and a to the k is a subgroup of them, the only possibility is that they're actually equal. So since one is a proper subset, one is a subset, but it has the same number of elements as the whole set, it can't be a proper subset. There can't be some additional element, some other element that's not in there, and so they have to be equal. Okay, so this is why this is a counting argument. We have that the subsuit generated by a to the k is inside the subset generated by a to the d, and then we're counting the number of elements of each of them, and we're seeing that they're the same, and so that means that they have to be equal. So this is one way to look at it. Now let's look at a more number theoretic proof. Again, let's clear the board. So for this proof, I'm going to use the fact that since d is equal to the GCD of n over k, this means that there exists some integers x and y such that I can write d as being n times x plus k times y. So again, this is a fact from number theory that if d is the GCD of n and k, then there is a solution to, in fact, there's infinitely many solutions to n times x plus k times y equals d in the integers. Well, what this means, if I now reduce both sides mod n, well, I have an n right there and a multiple of n right there. So when I reduce both sides mod n, that kind of disappears. Or saying this slightly differently, this means that if I do d minus ky, I get a multiple of n. And so then this means that this is exactly the definition, since n divides, d minus ky, of d being congruent to ky mod n. And then if we go back and think about, well, what does this mean about a to the d versus a to the k times y? Well, since d is congruent to k times y mod n, these actually are going to be the same thing. Okay, and so this means that a to the d is inside. Since it is a power, we can get it by doing a power of a to the k. It is inside the subgroup generated by ak. So the subgroup generated by a to the d is inside the subgroup generated by a to the k. And then using the same argument in the last proof, we already saw this. The subgroup generated by a to the k is inside the subgroup generated by a to the d, because k is a multiple of d. And so since they're both subgroups of each other, this means that they're equal to each other. Okay, so we have two nice proofs of the second statement. And the second statement is very important. So what it means is that if you think about, if you have a cyclic group and you take a generator of it and you have some other power of it, well, then that power, the subgroup it's going to generate, depends precisely on what its GCD with the order of the element is. Okay. So now let's do some immediate corollaries of this. So first of all, in a finite cyclic group, the order of an element divides the order of the group, right? And so this is coming from that the order of a to the k is equal to n divided by the GCD of n and k. This right here is always a divisor of n. And so that gives us this corollary. Next, if we have A has order n, then the subgroup generated by a to the I is equal to the subgroup generated by a to the j, if and only if their GCDs with n are equal. And their orders are equal if and only if their GCDs are equal. And this just comes down to if the order of a to the I is equal to the order of a to the j, well then that has to happen because n divided by GCD of n and I is equal to n divided by the GCD of n and j, and that only happens if those two are equal. And then in that case, if those two are equal, then a to the I is equal to the subgroup generated by a to the I is equal to the subgroup generated by a to the GCD of n and I, which is equal to a to the GCD of n and j, which is equal to the subgroup generated by a to the j. Okay, so all that's important in this is what the GCD of the power is with n, with the order of a. And then lastly, for this slide, this last corollary on the slide is just specifically plugging in, taking the last corollary and setting I to be equal to 1. And that means that if we set I equal to 1, that means that the subgroup generated by A is equal to the subgroup generated by A to the J, if and only if the GCD of n and j is 1, and that's because the GCD of n and 1 is always equal to 1. So this is just taking that last corollary and just plugging 1 in for I. Now, if we apply this specifically to the integers mod n, so recall that the integers mod n, we can think about this as a cyclic group generated by 1, where in this case, so we're doing this with addition, the order of 1 is equal to n. We can add 1 to itself n times, and that's when we get back to the identity. And so this corollary is just applying this specifically for the case that our group is z mod nz, and that's generated by 1. And so the k as a generator is going to be a generator for z mod nz with addition if and only if the GCD of n and k is equal to 1. Okay, and so let's do a quick example of this. So claim is that 7 is a generator for z mod 12z, because z is relatively prime to 12. And so in this case, since we're looking at addition, since we're using addition as our operator, we're really looking at the multiples of 7. And so the subgroup generated by 7, well, the first multiple is 0, and then we have 7. And then if we add 7 again, we get 14, which is congruent to 2 mod 12. And so 2 really is our element there. And then if I add 7 to that, I get 9. And then 7 plus 9 is 16, which working mod 12 gives us 4 mod 12. And then 4 plus 7 is 11. Add 7 again, we get 18. Reduce mod 12 gives us 6. And then 7 plus 6 is 13, which gives us back 1. And then 8. 7 plus 8 is 15, which we then reduce mod 12. So 15 mod 12 is 3. And then add 7 again, and we get 10. Add 7 again, and we get, let's clean this up a little bit. And now let's change that 14 into a 2. And so now we can go back. 7 plus 10 gives me 5. 17 minus 12 is 5. And then if I then do 7 plus 5, that gives me back 12. And so that cycles through. And so we can count how many elements are in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 things in here. If you don't believe me, we can start at 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 0. So they are all there. It's out of order because we're doing this based on multiples of 7, but they are all there. So 7 is a generator for Z mod 12Z. And we could do the same thing with any other number that's relatively prime to 12. So we also have that 5 and 11 and 1 are also generators, because those are the elements that are relatively prime to 12. Okay, now here's the big theorem. Really, this big theorem is just relying heavily on the last theorem that we proved, but this is the one that's going to tell us what our goal was. This is going to help us meet our goal for this video. If you have a cyclic group, you take any subgroup of it, then that subgroup is also cyclic. And so the proof of this, actually, we've already done all the heavy lifting. We just need to to put all of our ducks in a line and see it. So first of all, if our subgroup is just a subgroup generated by the identity, well, this is the trivial subgroup. And it is cyclic because it's generated just by the identity. So now let's suppose that our subgroup is not trivial. So let's take a non-trivial subgroup of A, excuse me, and we'll call it H. Well, so since H is a non-trivial subgroup, that means that there exists some A to the K that's inside H, with K not equal to 0. That also means that we can take, any integer power of A to the K, positive or negative, and so this means that A to the H has positive powers of K, because once we have some power that's non-zero, then we can take any integer multiple we want, and so if A to K was negative to begin with, then A to the minus K would be positive, and that would be an H. And so we know that H has positive powers of A, and so we can pick the smallest positive power. So let's let L greater than 0 be minimal, such that A to the L is inside H. So L is the smallest positive power that is inside H. And then let's let A to the M be any other element inside H, right? So H is a subgroup of this group generated by A, and so everything in H is also a power of A. Okay. And so this means, using the division algorithm, so by the division algorithm, I can write M equal to L times Q plus R, where R is at least 0 and strictly less than L. And then my claim then is that A to the R has to be an H, because R would be equal to A to the M times a to the L raised to the minus Q. And so since a to the M is inside H and a to the L is also inside H, then by closure, the product of a to the M times a to the L to the minus Q would have to be inside H. And so that would give us back a to the R. But since L is the minimal power, minimal positive power that's inside H, this means that R has to be equal to 0. So L divides M. Okay. And so a to the L is the smallest positive power of an element in here. If I take anything else in the group, it looks like a to the M. Well, then that power has to be a multiple of L. And so then this means that a to the M is inside the subgroup a to the L. And so since this is true for all H, this means that H is a subgroup of a to the L, which is a subgroup of H to begin with, and so they have to be equal. So this non-trivial subgroup H that we started off with is generated by a to the L. And so since this is any non-trivial subgroup, this is always going to work. Okay, our next theorem now. So now that we know that any subgroup of a cyclic group is cyclic itself, what can we then say about it? And it turns out that if we start off with a cyclic group, all of the subgroups generated by it have order that are also divisors of n. And this really is at this point, this really is a corollary of everything that we've proven so far today. So let's see that. So let's let H be a subgroup of the cyclic group generated by A. And so by the last theorem, this means that H is equal to a to the L for some L. And so then what's the order of H? Well, it's going to be n divided by the GCD of n and L, which divides n. Okay, so that tells us that any subgroup's order divides the order of A. And then on the other side, if we take each positive divisor k of n, so if k divides n, then you can see that a to the n over k, the order of this subgroup, is going to be equal to n divided by the GCD of n and n over k. But the GCD of n and n over k is just n over k. And so this is really n divided by n over k. And doing the algebra quickly, that's going to give us back k. So that is our subgroup of order k. On the other hand, if you have any other subgroup that has order k, so if the order of a to the I is equal to k, well, then this means that the GCD of n and I is equal to n over k, which, using the corollaries that we have, means that a to the I, the subgroup generated by a to the I, is the same thing as a subgroup generated by A to the n over k. Okay. So really this theorem is just, it's just collecting together everything that we've talked about so far in this video. So let's close this video out, and let's apply this especially to Z mod 12Z. Right? So we want to know what all the subgroups of Z mod 12Z are. And from what the last theorem tells us is that the subgroups are going to correspond to the divisors of 12. Right? So what are all the divisors of 12? So there's 1, 2, 3, 4, 6, and 12 is the last one. And so there's going to be one subgroup generated, one subgroup of order that's equal to each of these divisors. So the subgroup that's order 1, that's going to be just the identity. The subgroup that's order 2, well, that's going to be generated by 12 divided by 2. And so this is just the subgroup generated by 6. So it just has 0 and 6 in it. The subgroup of order 3, well, so that's going to be generated by 12 divided by 3. And 12 divided by 3 is 4. So it's going to have 0, 4, 8. And then if I add 4 one more time, I get back to 0. The subgroup generated by 4, well, that's going to be generated by 12 divided by 4. And so this is going to be 0, 3, 6, 9. If I add 3 again, I get back to 12. The subgroup of order 6 is going to be generated by 12 divided by 6, which is 2. And so 12 divided by 6 is 2. So it's 0, 2, 4, 6, 8, 10. And then last but not least is the whole group. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what's interesting about this is that if you look at this, looking down these divisors down on the left, if something divides a number further down, then its subgroup is actually a subgroup of that. So what do I mean by that? Well, so 2 divides 12, but 2 also divides 4. And so if you notice, 0 and 6, that is a subgroup of 0, 3, 6, and 9. 1 divides all of them, so 1 is a subgroup of all of them. 2 also divides 6, and 3 divides 6. And you have 0 and 6, 0 and 6 are inside there. 0, 4, and 8, 0, 4, and 8 are inside there. The subgroup of order 2 and the subgroup of order 3 are both subsets, are both subgroups of the group of order 6. And then all of these now are subgroups of the group of order 12. Okay, and so this is what's called a subgroup lattice. I actually might have done this a little bit upside down from the way this is normally done. Often you would have the whole group being up on the top, and then you have the trivial group being on the bottom, and then you have the subgroups getting bigger as you go up. But what the lines here represent is that this line here represents that 0, 4, 8 is a subgroup of 0, 2, 4, 6, 8, 10. And then if you look at 2, 2 divides 4, so it's a subgroup, and then 4 then is a subgroup of 12, so this means that 2 is also a subgroup of 12. Okay, and so this is sort of a kind of you might think about this as a graph way of breaking down a group into subgroups, a directed graph. That is all for this video. I will see you again soon.